the airport pavement design, and though in the last lecture we know that there are different pavement design that has been used previously and also being used in some other part, but this method that I am going to discuss today is something that is gaining not only popularity, but it's also uh, not only popularity, but it's also being mandated by Civil Aviation Authority for pavement design of airports all over the world. So this method is known as a far field, that is a FA pavement design method, Federal Aviation, and it is abbreviated as far field. It was, it was there in your textbook as well, but the latest version, the latest is from, it was revised in 2008, and it has got new methodologies for rigid and flexible pavement. It is dependent on the software design procedures, and not only that, but it also addresses the modern airplane parameters. So actually, what is far field? Uh, F stands for Federal Aviation Administration. Then R is rigid. Again, F is flexible, iterative, elastic layer design. It is the new method. It is previously we had LED FAA. Now this has been changed like this to this modern method. Was released in 2009, and the current version we are actually teaching here is 1.305, and that was released on 18th of January 2011. So for us it's 10 years old. Now, how does this pavement design method look like? Again, any pavement design method, there is always the soil investigation and evaluation. So this obviously is no different. And if you look at this context, the soil parameter for flexible pavement is measured in terms of subgrade modulus E or CBR, and this is the design value. You have one standard deviation below the mean. The lowest practical value on which a flexible pavement can be placed is CBR3. If you don't have this value, you have to stabilize or replace before laying a pavement on it. Now, in the context of rigid pavement, we have modulus of subgrade reaction, K value, and this is a design value and a conservative selection. The word conservative means the lowest possible values, because if you take the lowest possible value of K, it would mean that you will be over designing it. But never mind, airport, even an airport infrastructure or the aircraft, the value they cost is much more than the value you spend on the pavement itself. So if God forbid the pavement fails, especially in airport, that will be a disaster. So we go for the conservative selection of the K values. If we do not have the direct measurement of K value, you can always use this correlation 1500 CBR 26 raised to the power 0.7788. And this is taken from ASHTO 2002 method of pavement design. And since we don't have K values, so this is a better estimate of the K values. Now, when we say a pavement design, this current method of far field method covers standard pavement design procedure for both flexible and rigid pavement. It applies to pavement design for airplanes with gross weights exceeding 30,000 pounds, and the design procedure requires the use of computer program, that is far field. And if you look at this screenshot, this is how your software look like. And again, this is also in your book. So if you go to the pavement design chapter, you will also find this in the book. Obviously, the window will be of the older version. Now, in this design method, obviously the pavement design requires the traffic and the subgrade values. In this pavement design method, all types of anticipated aircrafts, we have used traffic here, but actually traffic means the cluster, the group of vehicles. Here your vehicles are your airplanes. So don't be confused that this method will be used for designing of highway traffic. It's not highway traffic, it's an airway traffic. The features is that obviously the features of the software is that all anticipated air traffics are included in the model. It is based on the cumulative damage factor, CDF, and this CDF is evaluated by summing the damage from each of the aircraft based upon its unique pavement loading characteristics and location of the main gear from the center line. And you can understand that the aircraft load is 95% on the main gear, or you can say the wheel beneath your engines, that is the landing gear. And we always design the pavement, the airport pavement, on the landing gear, and because it has got 95% of the total load of an aircraft. Now what you do, CDF can be defined as the number of applied load repetitions to the number of allowable repetitions to failures. And when you have got CDF1, it means the design life is exhausted. I'm sorry. And how does this software do? It keeps on making trial and error values till the CDF become 1. When I say trial values, it keeps on plugging different values of the surface, the base, and subbase, and until they reach the value 1, the software gives you the answer. Whatever is your design life and what should be your payload. Continue with this traffic model and cumulative damage factor. This CDF is calculated for each 10-inch wide strip over 12 over a total of 820-inch width. The gear location and the wander considered for each aircraft, and there is a rule called minus rule to sum damage for each strip. It looks like this. You can see there are a number of aircraft like Boeing 747, Boeing 777, DC-8, and the red line shows cumulative damage caused by all of this factor, and you can see this value 1, this value 1 is tangent to the cumulative value, and there you see your final section. Currently, this program continues, incorporates 198 traffic model. Each model is unique with respect to the gross load, load distribution, wheel spacing, and tire pressure. Then we also consider the pass to coverage ratio. And when you know that the lateral movement is known as the airplane wander and is modeled by a statistically normal distribution, the standard deviation is 30.4335 inches. The pass to coverage ratio is the number of trips along the pavement for a specific point on the pavement to receive one full load application. For rigid pavement, one full stress application to the bottom of the PCC layer, and for flexible pavement, one repetition for maximum strain at the top of the separate layer. This traffic model is based on 6C, uses the concept of effective tire weight. For a rigid pavement, effective weight is defined as the surface of the pavement equal to tire contact path, and flexible pavement effective weight is defined at the surface of the separate layer. Like any other pavement design, this pass to coverage ratio gives you this stress ball in this manner. Tire weight, effective tire weight, and you can see the height, what is the stress level or stress bulb at height each, and if your spacing, tire spacing are nearer, then there is an overlapping of the stress. Obviously, this will need a greater depth of the pavement. The airport pavements are generally constructed in uniform full width sections. For variable sections are permitted on runway pavements. The practical feasibility is that the complex construction operations, and then economic feasibility is the cost of complex constructions. So generally, even though people in the past used to have non-uniform width sections, and it can still be recommended, but with the problem of construction complexity, people are now thinking of full width uniform section, and these are actually now being recommended in this far-field pavement design as well. As you can see, these are the variable sections. This is half side. We have a PCC pavement, and then there is slight reduction in width that comes to be 0.7 T, and then the thickness here is 0.9 T, then it reduced to 0.7 T. So whatever, if the T is the thickness, for instance 3 is your thickness is say 50 inches, this will be 45 inches, and this will be 35 inches. So that is what this will what 70% actually of 70% of 50 is what? 35, I guess. So like this 0.70. So in a rigid pavement section, it is typically a Portland cement. Then there's a sub-base course and the subgrade. Now that sub-base course needs stabilization when airplanes exceeding 100,000 pounds are present in the traffic mixture. These are the different materials that are used, can be used for surface, sub-base and subgrade. You can select any of them. So to summarize the rigid pavement design, you required an input variables, the subgrade support conditions in terms of K value or modulus, material properties of each layer, modulus for all layers, flexural strength for PCC, thickness for all layers except surface PCC, Poisson ratio fixed in far field. The traffic, it is frequency of load applications, and the airplane characteristics in terms of wheel load, wheel location, and tire pressure. Obviously, this I have shown you before how you can convert the CBR value into in terms of K value of, and K value is the foundation modulus of the subgrade in terms of PCI or in terms of pound square inch per inch. As far as this sub-base layer is concerned, you have different options. Far field allows you to use 3 sub-base layer of different materials. The aggregate layer modulus is depending on the thickness, and these modulus are calculated by far field based on the thickness. Anyhow, 4-inch minimum thickness must be there. This is again the repeat of what we were saying about this material. For the Portland cement concrete, that is a surface layer, you use flexural strength around 600 to 700 psi, even though far field allows you to use 500 to 800 psi as well. And this flexural strength is based on the single beam loading with third point loading. The modulus is fixed as 4 million psi. The minimum thickness of any airport or runway should be at least 6 inches, and all thickness are rounded to the nearest 0.5 inches. So either you will have 6.5 inches or 7 inches. You may not have 6.25 inches or 7.25 inches or even 6.75 inches. So it's always 0.5 in a sense. You see this design flexural strength versus P1 specification. So that's why P1 has got 5% greater than value. So if you have actually calculated 650 psi, far field will take this as 680 psi. Factor to consider is the capability of the industry in particular area to produce desired strength, flexural strength with cement content. You need to avoid high cement contents, and where the early operations are necessary, you use a low strength than 28 days. So again, a brief look on the pavement design software. 198 models. Wheel load determined automatically based on the cross weight. There is an aircraft library, so if you input any of the aircraft, it will know what are the wheel locations and as well as the tire pressures. How? So the concept of annual departure is also present, and since we design the maximum load of aircraft is when it is leaving. So departure is always considered, though arrival traffic can be considered, but it is generally ignored because again we go for the idea is a conservative design, and the user determine percentage of the total airport volumes. The handling this craft, that is that single wheel, dual wheel, dual tandem. These are the grape, triple dual tandem and complex gear configuration, and it is results in the significant saving in computation time. Uh, you can see this, the window, the input. One is the structure window. You can just put your put your trials thicknesses in each of this window and the relevant K values like that. And on the right side, you will determine the you input the aircraft values. So there is a traffic value from this window and the other values of the materials as well as the thickness and the K value is you can define in this window. So that ends the first part of the far field pavement design. In the second part, we will discuss how to use a far field software. So that ends this part of the lecture. Let me finish it and we go back to